In this video, we're going to talk about something known as the average value of a function. Before we can do anything with it, we should define what it is. So let's write down the definition. The average value of a function f, or the average value of f of x, let's say, over the interval from a to b is defined to be the following. So we'll call it f sub ave to indicate that it's the average value of f. But what is it going to define to be? How do we compute it? It's defined to be 1 over b minus a times the integral from a to b of f of x dx. This is how we define the average value of a function, the average value over an interval. If we choose a different interval, we'll likely get a different average value, because as you can see, we're integrating from a to b, and you're also dividing by b minus a. b minus a, that's just the length of the interval. Length of the interval. Let's compute an example. Let's start with something very simple. Find the average value of f of x equals x over the interval, let's just say from 0 to 1, just to keep it simple. In order to compute the average value, we simply plug into the formula. So the average value of f on this interval is 1 over b minus a. Well, in this case, a is equal to 0 and b is equal to 1. So it's 1 minus 0 times the integral from a to b, the integral from 0 to 1. f of x is x dx. So this is the integral, well, it's 1 over 1 minus 0, so it's 1 over 1, or 1, times the integral from 0 to 1 x dx, which is x squared over 2 between 0 and 1. So that's 1/2. Therefore, the average value of x over the interval from 0 to 1 is 1/2. The average value does have a geometric meaning. Geometric meaning. And what is it? Well, let's suppose that our function is greater than or equal to 0 on the interval from a to b. That means that the integral from a to b of f of x dx is equal to the area under the curve. The average value, f sub av, is 1 over b minus a times this integral from a to b, f of x dx. So we can also solve for this integral. So solve for the integral. What does that give us? Well, basically we just multiply by b minus a, so we'll have f sub av times b minus a is going to equal this integral from a to b f of x dx. Let's look at this on a graph. We haven't actually specified a function at the moment, so we don't know exactly what the graph looks like. Let's say it's something like this. Y equals f of x from a to b. There's an a, there's a b. The average value is 1 over b minus a times this integral. So in other words, if you solve for the integral, as we've done here, we have that the integral from a to b is, well, I should write out the rest of it, of f of x dx is equal to the average value, I'm just rewriting the line above it, times b minus a. What is b minus a geometrically? It's the distance between b and a. And what is f sub av? It's a number. It's a number. It's the average value of the function. Suppose that we've computed it and we put it on a y-axis. So I haven't drawn in the y-axis, but let's imagine that it's over here somewhere. So let's say that over here is f sub av. So what's the point of this? Imagine that I draw a horizontal line. If I draw vertical lines here from that horizontal line to A and B, and I just fill this in, what have I established? What have I found here? I found a rectangle. We have a rectangle right here. Let's just fill it in, like so. But what is the significance of this rectangle? Well, the width of the rectangle is b minus a, and the height of the rectangle is the average value of f. So the area of this rectangle, the area of this shaded blue rectangle, is equal to the height of the rectangle, f sub av, times the width, which is b minus a. But that should look familiar. We've written that down somewhere else. That is exactly equal to the integral from a to b of f of x dx. But since f was assumed to be positive, this integral is exactly the area underneath the curve. So the area of the rectangle is the area under the curve. The area under y equals f of x over the interval from a to b. So you can see that this rectangle, which has height equal to the average value of the function, is equal to the area underneath the curve. So that's the geometric significance of the average value. We can see that in our example. So let's return to the example. So in this case, we're looking at f of x equals x over the interval from 0 to 1. So we already saw that the average value in this case, which was 1 over 1 minus 0, the integral from 0 to 1, x dx, we computed this and saw that it was equal to 1/2. So let's graph this. We're looking at the graph of y equals x, so it's a line at a diagonal at a 45-degree angle with the axes. So it should look something like that. And let's mark off something like, let's say that this is equal to 1 there. And so then this should also be equal to 1 because this, of course, is y equals x. The halfway point is right here. That's 1/2. So we saw that the average value was equal to 1/2. So let's just mark off y equals 1/2 on this graph. So then the area underneath the curve should be equal to the area of this rectangle. Now, in this particular example, that's quite easy to see because the width of the rectangle is 1 and the height is 1/2. So this is 1 by 1/2. So the area of the rectangle is equal to 1/2. Furthermore, we can compute the area underneath the curve very easily because it's a rectangle, not a rectangle, because it's a triangle. So the area of the triangle, which is the area under the curve, is going to be 1/2 the base times the height. But again, the base is 1, and in this case, the height or the altitude is also 1. So the area of the triangle, or I should say the area under the curve, is equal to 1/2, and you can see that they're the same. So that's our first example. Let's do another example. For this example, let's compute the average value of f of x equals, let's say, 4 minus x squared over the interval from minus 2 to 2. So for this example, we're looking at a parabola which is opening downward. So it's going to look something like, let's see, 1, 2, 3, 4. So this is y equals 4. That's the y-intercept. And we know that when x is equal to 2 or minus 2, those are the x-intercepts. So the parabola looks something like this. There we are. Let's just work on that side a little bit more carefully. There we go. That's good enough. So we're asking what is the average value of this function over the interval from minus 2 to 2. This interval is where f of x is positive, so that way we can look at it geometrically. So if you compute the definite integral from minus 2 to 2 of f of x dx, that's equal to the area under the curve. Again, over the interval from minus 2 to 2. So what is the average value? The average value from minus 2 to 2 is 1 over b, which is 2, minus a, which is negative 2, times the integral from minus 2 to 2 of f of x dx. But of course, we have a formula for f of x. F of x is equal to 4 minus x squared. So f av is equal to 1 over 2 minus a negative 2 is 4. Times the integral from minus 2 to 2, 4 minus x squared dx. This quantity right here that occurs in the denominator, that's just the length of the interval. And that's always true. If you go back to the original formula for the average value of f, b minus a is the length of the interval. Okay, so we can actually go ahead and compute this value here. Let's just rewrite it. F av, the average value of f, is 1 over 4 times the integral from minus 2 to 2, 4 minus x squared dx, which is 1/4 times the antiderivative, or an antiderivative of 4 is 4x, minus, and then we use the power rule, increase the exponent by 1, divide by that new exponent, between minus 2 and 2. So this is 1/4 times, so if you plug in 2, you're going to have 4 times 2 is 8, minus 2 cubed is 8 over 3. Then we're going to have minus, and now you plug in a minus 2, so 4 times negative 2 is negative 8, minus, negative 2 cubed is negative 8 over 3. So 8 minus 8/3 is, well, that's a full 8 minus a third of an 8 is going to be 2/3 8. So that's 2/3 8. Or, in other words, 16 over 3. This is very similar because now you have minus 8 minus a minus, so that's minus 8 plus 8/3. So this is going to give you minus 16 over 3. So you have 1/4 times 16 over 3 minus a minus 16 over 3. So in other words, that's 1/4 16 over 3 plus 16 over 3, which is 1/4 of 32 over 3. And that 4 cancels with some of that 32 and just gives you 8. So you end up with 8/3. So that tells us that the average value of f over this interval is 8/3. So if we think about that geometrically, if we find a rectangle which has base from minus 2 to 2 here, so let's actually just draw this down, or write this down, or draw it. We're going to have base from minus 2 to 2, And the height of this thing, 8 over thirds, that's approximately 2.66. Well, it's 2.66666 recurring. So if this is 2 right here, it's just about right there. Maybe I should make it just a little bit. So it's right about there, or so. Now the base of this is from -2 to 2, so it's going to look something like this. And the height of this thing, let me just try a little bit harder to make that straight. Something like that. Let's just make these a little bit straighter here, there, and there. Now the height of this is 8 over 3. So the area of this rectangle is the same as the area underneath the curve, like so. So that's the geometric interpretation. So far we've looked at examples where the function is positive, and the value to having a positive function is that you can have a geometric interpretation of the average value in terms of areas underneath the curve and areas of rectangles. But you can compute the average value for any function. It doesn't have to be a positive function. Let's look at another example. So for this example, we'll choose a function which is sometimes positive and sometimes negative. So compute the average value of f of x equals sine of x over the interval, let's say from 0 to 2 pi. This function, sine of x, is sometimes positive and sometimes negative on that interval. So let's compute the average value. F sub av is equal to 1 over 2 pi minus 0. That's the length of the interval. Times the integral from 0 to 2 pi of sine x dx. So this is 1 over 2 pi times the integral from 0 to 2 pi sine of x dx. We know an antiderivative for sine, namely minus cosine x, from 0 to 2 pi. So this is 1 over 2 pi times minus cosine of 2 pi, then minus a minus cosine of 0. Cosine of 0 is 1. Cosine of 2 pi is also 1, but that means we have 1 over 2 pi times minus 1 plus 1, which of course is 0, because minus 1 plus 1 is 0. So the average value of sine of x over this interval is 0. That's not really all that surprising. If we graph it, we know that sine is periodic with period 2 pi. And we know that it crosses the x-axis, which is here, at pi. So we know halfway between there it goes up to 1. Let's say that's right there. So that's positive 1. And so that's pi over 2. And then this is 3 pi over 2. And there it'll be minus 1, so it'll be right about there. And then it goes back up to 2 pi, or it goes back up to 0 at 2 pi. So the graph looks something, roughly speaking, let's try that one again, like this. So you can see that this function, y equals sine of x, has a graph which between 0 and 2 pi spends exactly as much time above the x-axis as it does below the x-axis. So that means the area above the x-axis is the same as the area below the x-axis. So it's not surprising that in this case we'd have an average value which is 0. One thing that you might notice, if you look at these pictures, in each case, the function actually attains the average value of the function. In this example we've just done, the average value is 0, and there are certainly plenty of places where sine of x is equal to 0. If you go back to our previous examples, you can see that the average value, that's where this blue line is, you can see that it passes through the parabola on 2 occasions. And in our first example, this horizontal line, which represents the average value, passes through the curve exactly once. This is not a coincidence. It follows from continuity, and this is something called the mean value theorem for integrals. The name should sound somewhat familiar because there is a mean value theorem for functions, and this follows directly from that. So this is the mean value theorem for integrals. And it's basically a statement about continuity. So here's how it goes. If f is a continuous function, on some interval ab, then there is some number c in this interval from a to b. And there may be more than one. So there may be more than one number, such that f of c is equal to the average value. We can easily see that in our examples. Examples from above. These are the examples we've already looked at. So our first example was f of x equals x over the interval from 0 to 1. And we saw that the average value in this case was 1/2. And sure enough, f of 1/2 is 1/2. So that means c is equal to 1/2 does the job. In this case, there's only one c value, but sometimes there are more. So for our second example, f of x equals 4 minus x squared. And in this case, we were on the interval from -2 to 2. We saw here that the average value of f was equal to 8/3. And if you're not sure about that, we can just go back and you can see it's 8/3. So what does that tell us? That tells us, according to the mean value theorem, which is what we're talking about now, there must be at least one c for which f of c is equal to 8/3. And actually we know that there are two, because if you go back to the picture, you can see that this line right here, which represents y equals 8/3, you can see it passes through the parabola twice. So that means there should be two values for which this is true. So we can just figure out where they are. F of x equals 8/3. Solve for x. Well, f of x is 4 minus x squared equals 8/3. So what we can do now is we can solve for x squared first. Minus x squared is equal to 8/3 minus 4. Well, you want to give these a common denominator, so you multiply by 3/3. So that's going to be minus 12/3. So that's minus 4/3. There's a minus there, but there's also a minus there. So x squared is equal to 4/3, and x is equal to plus or minus the square root of 4/3. Or if you prefer, plus or minus 2 over the square root of 3. But you can see that there are two values. And we knew that ahead of time. What about our third example, f of x equals sine of x on the interval from 0 to 2 pi? Well, in this case, the average value was 0. And there are certainly several places where that happens. If you look at our graph, sine of x is equal to 0 at the origin, at pi, and at 2 pi. So there are three choices for c. c equals 0, c equals pi, c equals 2 pi. There are, of course, other values for which sine of x will equal 0, but we're only interested in the values inside the interval. That's all we're interested in here.